Back to topic 8.4. Hopefully you stretch, grab a snack, get some water, whatever you need to do. But we have a lot more to go. I'm sorry. All right. So for this one, HClO2. You can tell I was not thinking correctly on the last little part. That is a weak acid, not a strong acid. My bad. So this page is dealing with, at least this little section, is dealing with a weak acid plus a strong base. And then we will see what happens with this one. Recall that in the last video for number, like this one, number 3, we had a weak acid and a strong base. Same thing for the other one. But, so all 3 of these were weak acid and strong base. However, in number 3, the weak acid was in excess. In number 4, we had the same moles of each one of them. So predict what's going to happen for this last little one. All right, so we've got the balanced chemical equation. I do know, however, that the Mg is going to be a spectator ion in here. So I'm not even going to add it in here. So I know I've got HClO2 plus, and I know I need to have 2 OH minuses, so I'm going to do that. That H is going to go there. But knowing that I need to have 2 H's for every, or sorry, 1 H for every 1 OH, I have 2 OHs, I should have 2 of those. So at the end, I have 2 waters plus 2 ClO2 minus 1s. And identify the reaction between. We know we have a weak acid and a strong base. Same titration curve as before. So this one, note, you have a little bit less space to write. You don't have as much to do, which is pretty cool. So step 1, find the concentration of H plus and OH minus after mixing. When you do the math for that, makes you end up with 0.0667 molar H plus, and you end up with 0.133 molar OH minus. So looking at this, we'll throw it into a BCA table. We have, the BCA. We have, let's see, the equation is 2 HClO2 plus 2 OH minus in equilibrium with 2 H2O plus 2 ClO2 minus. I know that it's like we've got coefficients of 2 everywhere in here, but it does matter in the grand scheme of things. So I just want to keep those 2's in there for right now. So I've got B, C, and then the A. Waters, of course, we're not going to do anything with that. The H plus is 0.0667. The OH minus is 0.133. It looks like our OH minus in here is excess. So we're going to write in here that, ding, 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 hopefully you got that right, that the strong base is in excess. All right. So 0.0667 minus 0.0667. We're going to add in, we're going to kind of keep those as our minuses for right now, because I know that I'm going to have that as my excess. So 0.133 minus 0.0667 gives us 0.0663. This is a strong base. If I have the concentration of a strong base, I can just use the pH square. So wherever that went from the opener. I have my concentration of OH minus. I need to get down to pH. So when you do that, hopefully, I'm not going to do the math for you guys here because you should be able to take care of that. Your pH ends up being 12.8. And let's think about that. That makes sense because you end up having more of that base. So therefore, it's going to be a higher pH at the equivalence point. So let's take a look down here. Side notes, 3, 4, and 5. How are they all similar? So we know that they end up having a weak acid and a strong base. But 3, 4, and 5 were different about what there was in excess. So I'm going to kind of put that in here, what you would do in each instance. So let's say your concentration of H plus is greater than your concentration of OH minus versus your concentrations are the same versus your concentration of H plus is less than your concentration of OH minus. All right, so what you would do in each instance. So first of all, you have the same exact first steps. So we would find concentration of H plus and OH minus for each one of these. Then your step 2 would be to do a BCA table. Same thing for these two. After you've done those, that's when it becomes a little different, right? So with our first example in this set for number 3, we use the Henderson-Hasselbalch when the weak acid was in excess. When a greater amount of weak acid, we use the Henderson-Hasselbalch equation. In example 4, we had equimoles of H plus and OH minus. So we put it into the Rice table. And then from the Rice table, we put it into the P square or pH square. So we'll say Rice and then pH square. For this example, where you had excess of OH minus, we just put it into the pH square. So whatever you do in here makes a difference. And we have to do these first 2 steps in order to figure that out. So let's take a peek at the next set of questions. So 6, 7, and 8 are kind of linked together. Here we have HI. That's a strong acid. Here we have a weak base. So these next 3 questions are dealing with strong acid and weak base. So we'll say strong acid plus weak base. So let's take a peek at what we do here. We have HI. That iodine, we have to think about, is it going to be a spectator or not? And in this case, yeah, it's going to end up being a spectator. And go back to Unit 4, I forget, maybe like topic 4.1 slash something. I forget exactly what, but we went through and we figured out what what the spectator ions would be. So use that to your advantage. So we've got H plus, NH3, and then that is in equilibrium to end up producing NH4 plus. I will throw, actually, I'm sorry. Let me do this. Let me just do the spectator ions in there. So we have NH4, HI and NH4I. We can also show that H plus is really going to have just a lot of water in it. So that H plus really is getting donated over here to the NH3. It's in equilibrium with NH4 plus and OH minus. So I know it seems weird getting that from there, but if anytime you have a base, add it with water, then you will see what that OH minus is going to be deriving from. So here we have a strong acid and a weak base. If we look at our number 5 from topic 8.5, we end up having that weak base. We knew it was a weak base because there was a little bit of a dip and then it leveled off, and that pH started a little bit less than 12. Here we're adding H plus. This is our pH. So again, you have a little bit of a dip, and then it scoots over there. So your equivalence point, your pH, is less than 7. So, just like we did with the other two, we're going to do the same exact thing here. We're going to find the concentration of H plus and OH minus. Same thing I'm going to have you guys do. Do the math on your own. Make sure that you end up with the correct answers. We're only going to learn if we do. So here, we ended up with 0.50 molar H plus, and we end up with 1.0 molar OH minus. Then we throw it into a BCA table, same exact thing that we've done for each and every single one of those other ones, with the exception of the strong acid with the strong base. So let's see. I'm going to use my HOH plus NH3. Yeah, I'll do that one. And NH4 and OH minus. I'm thinking because I have a weak base here, I'm actually not going to show that OH minus. So I lied. My bad. I'm going to get rid of this. And this happens. And again, I didn't want to show that OH minus because we do have a weak base. It's not going to be completely disassociated. So we do end up seeing kind of some of those, like we don't want to show that OH minus. So that's kind of counterintuitive, especially when we look at our data afterwards. BCA. So for HI, we ended up with 0.50 for our OH minus, which, yes, I know it says OH minus, but we're going to at least look at it like knowing that that NH3 is our base. So go with it, right? NH3 is our base, OH minus is kind of representing that, and we will stick with that. It looks like our weak our weak base is in excess. So we're going to subtract out those values. Because that's an excess, I know I'm going to add in some more of that NH4 plus in here as well. So 0.50, 0.50. I know this is a spectator. I'm just putting it in there just to make sure it's represented. So here we can say that the weak base is in excess. All right, so looking at the previous page, we can see that when we had the weak acid in excess, we ended up doing obviously the H plus and OH minus, the BCA table, and then the Henderson-Hasselbalch equation. We're doing the same exact thing here. Our weak base, in this case, is in excess. So because of that, I'm going to use the Henderson-Hasselbalch equation. So this equation looks slightly different. Not too bad, though. I'm going to say that the POH is equal to the PKB plus the log of my conjugate acid over my base. And just to remind ourselves, this is the acid, this is the base, this is our, we're going to say that, yeah, so our conjugate acid, and then this is our conjugate base. So our PKB, well, they gave us pKa in here. So we do know that 14 minus the pKb gives us the pKa. So the pKa, 14 minus 9.25, is equal to the pKa. So 14 minus 9.25 is 4.75. is equal to my pKa. And then I've got to figure out what that is for my Ka. So I know my Ka is equal to my my 10 to the negative pKa. So it's 10 to the negative 4.75. And let me put that in scientific notation. Okay, cool. So that is equal to 1.78 times 10 to the negative. Oh, wait, sorry. I was just going ahead of myself. My bad. I don't need to do all of this part because I'm not putting it into a rice table. I'm sorry. Sometimes you just kind of go on a roll. So let's see, your base, so yeah, we know that our HB, sorry, and I didn't do this in these other terms, my apologies. So this is our base, this is our plus sign, essentially, that we would end up having in here. Try to think of the best way to reroute this. So, okay. So you know your plus signs right here. This is what this one's equated to. And you end up with 0.50 over 0.50. Well, the log of 1 ends up being just 0. So, like, thinking through, like, the log of 1 ends up as 0. So your POH in this case is equal to 4.75. Then use your pH is equal to 14 minus your POH. So 14 minus the 4.75 ends up giving you 9.25. So looking at this is a prime example of when your pH is equal to your pK. So your pH is equal to your pKa. And that's what happens when you end up with that weak base in excess. That's the half of the equivalence point, apparently, for this one. But that's pretty cool. All right. Looking at number 7. Methylamine, not one of the bases that we had seen, so that must be a weak base. This HCl is a strong acid. So when we are looking at this, we can figure out, okay, what the equation is, what the reaction is, etc. I would hope that at this point you feel so confident that you can just attempt these on your own. And that would be absolutely amazing. I'm assuming you did. Great. So now we have started playing, and you have your weak base and your strong acid. So your strong acid is HCl. Your weak base is CH3NH2. We're going to have some equilibrium in here. We're going to have Cl minus, and then your CH3NH. I'm going to make that a 3. I can make it like another H on the beginning if I wanted to, whatever. But I'm just showing that I had that extra H right there. So again, I have a strong acid and a weak base. I'm going to make sure that in my packet, I know that this is a strong acid and a weak base. You can sketch that titration curve again. And let's kind of go through and run through the first two parts of this. So the H plus concentration and the OH minus concentration. Your H plus ended up being 0.065 molar H plus. Your OH minus ended up being 0.065 molar OH minus. So you know that your H plus concentration is equal to your OH minus concentration. Looking ahead, when that happened last time, when I had a weak acid, I had to go through the rice table and then the pH square for this one. So show that with your BCA table. And your BCA, you have HCl, CH3, and H2 in equilibrium with Cl minus and CH3 and H3 plus. BCA. All right, so we have 0.065, 0.065, 0, and 0 for each of these. We're going to subtract out 0.065 for each of those. And we're adding it over here to your conjugate acid. And this one's a spectator, so we don't really quite care about that. Here, and here. Cool. So then you've got rice and pH square. So let's take our rice table. This time I'm going to take this this conjugate acid and I'm going to add it to water so we can kind of see at the end how much of the H3O plus we end up having. So again, this part's a little different. I'm going to go a little bit more not detailed, but slower for this part for you guys. I'm adding this to water, and then we can see what ends up happening at the end. So if you even want to make a note, when you have equimolar of both, for the rice table, add your conjugate acid to water, and then see what you end up with. This extra H plus is coming over here. So I have H3O plus and CH3 and H2. Water is not in our equilibrium expression, so we do not need that. I am taking this and bringing it over here. 0.065. I don't have any initial of either one of these two because I'm reversing the equation right now. I might change. So this is the base. I'm going to do minus B. Oh, actually, yeah, no, this one is an A. Sorry, that's an acid. And I'm going to do plus acid right there. And that's what I'm showing, like that. This is the conjugate acid, so that's why I'm adding it to water to show what that H3O plus is. All right. So I've got 0.065 minus A, and then I am going to put it into a Ka expression. Hopefully you can do these in your sleep. Okay, cool. All right, so from up above, I have a Kb is equal to 5.0 times 10 to the negative 4. So I've got to think about my expression. So if I want to think about like what might happen, or how do I figure out my Ka? I know my Ka times my Kb is equal to 1.0 times 10 to the negative 14th. So my Ka is 1.0 times 10 to the negative 14th over 5.0 times 10 to the negative 4th. I think. Sorry, I'm trying to mental math this. I want to say it's 2.0 and then 11. Let me just double check that. And remember, 1 EE negative 14, close out that parenthesis, divided by 5 EE, oopsies, EE negative 4. Cool. So 2.0 times 10 to the negative 11. So let's stick those in there. 2.0 times 10 to the negative 11 equal to, we've got a squared at the top, 0.065 minus a. Assume a is negligible. Cool. When you do that, do the math on that. I'm doing the math as well. All right, end up with Okay, let me just double check. Okay. 2 to the negative 11 times 0.065, and then the square root of that, 1.14 times 10 to the negative 6th. All right, and that is essentially your H3O plus. Woo, so that's not too bad to get the pH. Negative log of 1.14 times 10 to the negative 6th. So negative log of that answer ends up being 5.94 for that pH. Phew. All right, cool. So does this make sense? You've got a strong acid and a weak base. So our equivalence point ends up being lower than 7. So yeah, that part makes sense. All right, and number 8. So we've dealt with something where we have the strong base in excess. We have equimolars of those, so likely that this is going to be our, sorry, my pages are all over the place at this point. So we have, okay, cool. We've had the weak base in excess. We have H plus and OH minus that are equal to one another. This one we end up should likely very likely have the strong acid in excess. So we're going to use the same reactants that we did before. We have the strong acid of HI, hydriodic acid, and NH3, which is ammonia. That's essentially equivalent to what you use for cleaning windows. So think through what the equation would be at the end of this. So we have our, I think it's like the best way to show you this. Okay, yeah, I'll just kind of stick to what we've been doing. So NH4 plus iodine. So we can see that we have water plus NH3 in equilibrium with NH4 plus and OH minus. All right, so this reaction again is between a strong acid and a weak base. So make sure we make a note of that. Strong acid plus weak base. All right, so step 1, the concentration of H plus and the concentration of OH minus. We end up, let's see, I think I did this one. Okay, cool. So 0.75 molar for H plus and 0.5 molar for OH minus. 2 is our BCA table. So we can use, let's see, I think the best way to do this for you guys. We can do our, so because we know that we end up having more of our strong acid, it's actually very equivalent to just having like a reaction that goes to completion. So I'm going to show you this one here. It's essentially H plus and OH minus producing H2O. Again, because our strong acid was in excess. I can't do this unless I have that. So we have to be very, very, very careful about what we do. So 0.075, 0.50, that's 0.25. So we know we have 0.25 molar of our H plus, and then therefore we could use the pH square. So here we can say that pH is equal to the negative log of your H plus concentration, which is 0.25. So that should be equivalent to negative log 0.25. Oh, 6. Actually, give it to me in scientific notation. So 0.6 6,0 is my pH. All right, cool. So let's talk about all of these. 6, 7, and 8 had a strong acid and a weak base. Each of the instances. So if I go back, number 6, I had weak base and excess. So I'm going to do the same kind of categories here. And then OH minus for each one of these. So for this one, I had weak base in excess. So I had a greater amount of OH minus, and that was for number 6. So we did the same exact thing for each one of them. We found concentration of H plus and OH minus. Then we put it into a BCA table, which we did for each of these. This one, it ended up being a little different. We just used the Henderson-Hasselbalch equation. For number 7, we found that we had the concentrations equal to one another. So those were equal. For this one, we had to do the Rice table and pH squared. To make a note with that Rice table, we had to flip equation and add water. So that's what we did here. And then the last one, the excess, so the strong acid was in excess. So here we could just put it into the pH square. For the BCA table, we had to show the H plus OH minus. So that might be a little note to make for yourself as well. And then we can kind of go back through for 3, 4, and 5, what we did a little differently. And do those. Let me see if I can find all my papers, which are all over the place. Okay, yeah, cool. So for my first one, where I had a greater amount of weak acid, I just kind of kept that equation the same as my net ionic. That was cool. And then when I had excess of strong base, I used my product and added that to water. So that's how I did my BCA table. I did flip the equation and add water. For this one, and then for I'm sorry, that was for my Rice table. Flip equation and add H2O for the Rice table, not for the BCA table. And for this one, I had to show that I had HClO 2 plus my OH minus. So I'm showing where I don't think there's much I need to switch on that one. Nope, I didn't need to switch anything or do anything funky for that one. All right, this is a lot. I get that. We've got 2 massive videos on this. But notice the patterns. Chemistry is all about patterns. And when you can figure out the patterns as opposed to going blindly through them or through the work, you can see that it actually does tend to make a little bit more sense. And we want you to be sense makers, not just the people who kind of go along with everything. All right, go take a break, take a nap, go take a walk, do some exercising. Bye, guys.